service. So this is a project that me and two other developers have been working on, and we called it Prefixy. And basically what it is a hosted prefix search service that can power a Google-style autocomplete. And the idea, what we thought was neat, is what if you were able to take like just a little front-end client JS snippet and be able to add a dynamic Google-style autocomplete to basically any input field. So I think the best way to kind of show what it is just by showing it. So let's say we start typing Microsoft, right? So it kind of works how you would expect an autocomplete to work. With each keystroke, suggestions appear that match the prefix you've typed in so far. And so that works fine, but obviously nobody has typed in Microsoft before. And what makes this dynamic is that once a new completion is entered that hasn't been entered before, it will grab it and add it to future suggestions when people type in that search bar, right? So, for example, currently Microsoft for the character just M, we don't see it yet, right? Because these other suggestions have a higher ranking, meaning that they've been more popular in the past than what we just searched for. But if we type MI, Microsoft ranks higher for that. These other suggestions aren't really that high ranked. But if we type Microsoft again, or we select it, it basically treats it as a vote of confidence. So now for MI, it's higher. Let's see if we can get it to rank. Okay, we're starting to see it pop up for the letter M, right? So pretty straightforward. Now Microsoft is the number one suggestion for typing the letter M, because I've been sitting here typing it in a lot. So you can imagine if people are using this service and typing things in, the things that are typed in the most will be what start floating to the top. So that's what it kind of looks like in action. So the 3 bullet sort of summary of what it is, it's a hosted prefix search engine that powers autocomplete suggestions, and it dynamically updates and ranks those autocomplete suggestions based on user input. And the idea is to have it be an easy to use service for app developers to just add autocomplete to any field on their apps or websites. We already did the demo. So what will I kind of be covering today? So I'm going to cover what we prioritized during the research and development stages of this project, how we thought about the trade-offs as we design and build the system from scratch, how we thought about choosing the right data structures and algorithms based on the requirements that we had set out for ourselves, and how we would build a system to have enough flexibility to accommodate a lot of data if potentially a lot of people end up using it. So there's some terminology that we used when we were building this project, and just to kind of get us all on the same page, I want to cover those because they'll be coming up a lot. So a prefix is basically kind of what you see when you're typing in, right? So as far as you've typed into an input field, that's going to be the prefix. All of the strings that could complete that prefix is what we call completions. And each completion is associated with a score, which is its relative rank or popularity for other completions for a given prefix. The completions that we then actually send to the front end to be rendered are what we call suggestions. Basically, we're not going to show every possible completion, right? You only have a limited room, and we only want to show the best suggestions for a given prefix. And then we have this notion of a selection. So kind of like as I was submitting Microsoft, that would be a selection where basically it's kind of almost like a vote for that completion, that this is something that I've searched for. So what were our design goals when we were building this thing? So we had 2 primary requirements, and one was that it has to have lightning fast reads. The idea being that for an autocomplete to be useful and to work the way or kind of deliver the value that it promises, is it has to be quick and it has to respond quickly to every keystroke. And the other thing that we need is that the suggestions that we return to the user should be dynamically ranked and relevant. So the idea being, again, that we want to bring popular searches up and have those kind of outcompete things that are rarely typed in. So this had a couple of implications for us. We wanted to prioritize the speed of reads kind of for any trade-offs that we were looking at. We also needed some sort of ranking algorithm to kind of accomplish the ranking of popular suggestions. All right, so when we're thinking about data structures and algorithms, one of the key things we thought about was if we have a ton of data where a lot of people are typing things in, maybe we have like thousands or millions of completions that we're handling, what kind of data structure and what algorithms will support really quick searches for our project. So there were 3 measurements we considered for big O, and I'll just kind of cover them here, but we'll see them come up a lot later. So N is the total number of completions in our data set, right? So if we have 1 million completions that we're wanting to potentially offer as suggestions, N would be all of the ones that we have in our data set. K is what we're calling the number of completions for a given prefix. So for example, all of the strings that we store for the prefix CA, those would be, that bucket would be all the completions for CA. And that's what we're calling K. And then L is the length of a string that we're looking up. So if we're looking up CA, the length of that would be 2. And so that'll be something that will come up in some of these things we looked at. So let's say we've got these words here. These are fun words with good scores. Cat is very popular, coin not so much. So the question is, how do we store suggestion or completions like this in order to be able to retrieve them quickly? So we first thought, well, why don't we just go with a really naive approach and just have a hash of all the completions, right? So we can have our completions as keys with their associated scores as values, which is pretty fine. Except we'll have a bit of an issue with it. It's pretty space efficient, right? It's as much space as you have completions, as well as for the hash table to accommodate a load factor to avoid collisions. So it's fine from that perspective. But let's say we try to do a search, right, for a given prefix. So let's say we're looking for everything that starts with CA. So the first thing we'll have to do is go and visit every single completion in our data set and examine it to see if it's a potential completion that begins with CA. So for each completion then, we'll have to go and probe and check if it starts with those characters. And then once we've kind of found everything that starts with CA, so like car, cat, and cart were all matches, we've pulled them out, but now we need to sort them by their score to be able to return the most popular ones. So this won't really do for us because we're ultimately bottlenecked by N. I mean, L and K are relatively small, but obviously if we have millions of completions, just to find like the handful that we want to return that match CA, visiting all of them is just not realistic, and it's going to break the requirement that it should be really fast. So there's another data structure that we found that ended up being a really great fit for our particular problem, which is called a trie. It's a tree-like structure where all the words or strings are basically mapped by character, where children under a given parent node will all share the same prefix. And what's great about this is we can go to a given prefix in O of L time, like the length of the string that we're looking at. So let's try to look for everything in a trie that starts with CA. So first we got to find the prefix. So we'll go down to C and then CA, which is nice because that's just 2 steps. But then we still have to go and find all the completions under that node, right? And technically, in the worst case scenario, that's O of N, because like let's say somebody only typed in the character C, we would have to visit all the nodes below it, gather them up, and then we still have to sort them to be able to rank them by popularity. But what's cool about the trie is that there's a simple optimization that we were able to make here that is actually going to allow us to get rid of O of N. What we can do is for a given node, we can store all of the completions that begin with that prefix in that node itself. So obviously this takes up space, but for our use case, time is precious and space is cheap, so we're very happy to make that trade-off, right? We can just store all of the completions in each node, and now we don't really need to worry about O of N, right? If I'm looking for everything that starts with CA, I can just go right down to that node in O of L time, and then just do the sort. But there's actually a couple more optimizations that we can do to actually get us to constant time, which is great because it means that as things grow, we'll be able to keep up. So one of the things that's kind of natural as you're typing is like nobody's really sitting there typing an essay into a search field. So we don't actually need to store every single possible prefix for a given completion or string. So like let's say we have the sentence, Tyrannosaurus rex is a pretty large dinosaur, but certainly not the largest. That actually has a lot of prefixes in it, right? If you think about slicing all of that up. But realistically, somebody's only typing in maybe 10, 15 characters, and they'll be able to select what they're looking for from that. If it's not there, then this is probably like some long tail search that's fairly unlikely to happen. So we can still save those long tail searches, but they will just all share like the longest prefix up to maybe say 15 or 20 characters. So in that way we can hold L constant, or know that we'll never exceed a certain number of steps to traverse to L. The other thing we can do is limit our completion bucket size, which is K, the number of completions that would match any given prefix. Because we only need enough to support our ranking, right? So like when you're typing in and you're getting like your 5 or 10 results, I don't need to have to show all the 300-400 possible completions that could complete that prefix. So we can limit it to some reasonable amount. We still want enough to be able to have a ranking algorithm working in the background to rank them, but we don't need to store every single completion in every single node. So by collapsing these down, by keeping L and K constant, we can actually get to O of 1 time. Now, sort of our final iteration on this was we found this data structure called the prefix hash tree, which is really cool because basically you can take every node in a trie and you can map it to a key in a hash table. So you have your keys representing the prefix in our case, and then all of the values can be the completions that match that prefix, which is also great. We still have O of 1 access to any given prefix and its completions. And the other thing that's really nice about this is that it now maps nicely to a key value store like Redis, which we'll talk a little bit more about later. But yeah, so this was kind of our final data structure that we chose for our project. So we kind of started out at the naive hash. We were bottlenecked by O of n, basically all the possible completions that we have. We then went to a trie, which gave us a sort of shape, a new shape that we could work with, where we were able to create an optimization by saving the completions within each node in the trie. And then by holding L and K constant and implementing with a prefix hash tree, we're now in constant time. So no matter how much data we have to, or how many completions we hold in our system or in our data set, we'll always be able to, from a data structure perspective, return the completions in a very timely manner. Yeah, so everything beyond this is really implementation details, because that's kind of the core that is going to make this service work. So I mentioned Redis earlier, and we use Redis to implement the prefix hash tree. So why do we choose Redis? Well, Redis is an entirely in-memory data store, so that's going to meet our performance requirement, because reading from memory is a lot faster than reading from disk. And Redis actually offers some really nice data structures for managing our completions. So like up to now, these completions have kind of looked like little set or little arrays, but we actually haven't really defined what data structure we want to use for those. So which Redis data structure should we use for the completions? So one thing to think about is that our two primary things that we're going to interact with Redis is a search, where we're basically looking for completions for a prefix, or an increment action, where we're going through trying to find a completion that was selected and bumping up its score in the ranking. So keeping that in mind, the first Redis data structure we looked at was the Redis list. It's basically a linked list. Redis under the hood implements it as a doubly linked list, so you get nice O of 1 access to the head and tail nodes. You can get to the other nodes in O of K time. So it seems pretty good on the surface. So for the key H, this is the data structure value that Redis would have. So let's do a search. So we issue an L range command to Redis for the letter H, and to grab the first 5 nodes. And we get those in O of 1 time, which is pretty good. That's actually kind of what we want. However, let's say we're trying to increment something, right? So the Redis list doesn't give us any guarantees in terms of order or ranking. So we basically have to do all that ourselves. And so first we would have to go and issue an L range command and grab every single completion for our prefix. And then we would have to do a binary search to go and find that completion that we're trying to increment. So we're trying to turn happy from 29 to 30. And then we have to do another binary search because happy is now out of order, right? Like if we're thinking of it lexicographically, happy 30 is now in a higher ranking than help 30. So we need to do another binary search to find where it belongs, which is also O of log k time. And once we've done that, we need to actually tell Redis to update those changes in the data structure. So we have to send a command to remove it from its current position. Then we need to issue an L insert command to put it where it belongs. So that's a lot of steps, a lot of round trips, and even from a network perspective, we're now having to issue more requests than we like. So the Redis list, the pros are it has an O of 1 search, right? That's great. But the cons are that we have multiple round trips per update. We're also doing things in our application in terms of the organizing and sorting of those completions, so that may cause concurrency issues. And also we have a large payload. We're bringing all the completions back every time to do our sorting, and we don't get any uniqueness guarantee. So Redis list, let's try something else. So Redis has a sorted set also. And the sorted set is really cool. This is sort of a visualization of it, but I mean, that's not really what it looks like. But for a key, say H, the sorted set is basically a number of elements with associated scores, which works out really well for the sort of problem pattern that we're working with in our project. So the sorted set under the hood is implemented with a skip list, which means you get O of log k time complexity for most operations, and it handles uniqueness and order for us. So if we want to do a search, that's going to take O of log k time by issuing a Z range command. And again, if we're limiting the size of k, this is practically constant anyway. And our increment function, we simply issue this Z inc or increase by command to Redis, which will then increase a given completion and update where it should be amongst the other completions. So the cons are, well, technically searches O of log k, which is slightly slower than the list, but not really because we're holding k constant. But it has a lot of pros, right? It's easier to work with. We've got fewer round trips, smaller chance of concurrency issues because Redis is handling all the sorting on its side, and smaller payloads because we don't need to bring everything back and organize it. And the uniqueness guarantee is nice because then we don't need to have any sort of deduping logic on our side of the application. All right, so I earlier mentioned that we're going to limit this bucket size, right? Like how are we going to hold k constant? And we actually got this strategy for maintaining a bucket limit while also being able to manage the scores from the creator of Redis. He had a blog post about it and recommended the following strategy, which we implemented and we were happy with. So let's say a user submits a search for JavaScript, and the bucket for the letter J is full, right? It's at the limit. We only want to store, say, up to 50 completions in that bucket. So we kick out the completion with the lowest score. And then we insert our new completion, so JavaScript, with the element that we removed score plus 1. And the reason why we do that is because one, we value recency, but two, is you want to give a new completion sort of a fighting chance, right? So if we gave it a score of 1 or maybe just 10, if somebody were to type another search that started with J immediately after this came in, it could boot it out and really never quite get a chance to actually climb in the rankings, so to speak. So this is how we maintain the bucket limit while still being able to provide a way to rank these completions. So obviously, what if we run out of memory, right? So Redis is all in memory, and we thought, well, there's also the reality that not all prefixes or completions are all that popular. So is there like a good strategy we can come up with where we persist some of these prefixes and their completions to disk? So we chose to use MongoDB to be able to store more than what we can fit in memory. And we can set an LRU eviction policy in Redis to kick out old prefixes and completions out of memory that aren't very popular. We still have them in Mongo, but they don't necessarily need to be in Redis. So we can have Redis act as a cache that'll have most of the prefixes and be able serve those up directly out of memory most of the time. And if it doesn't, then we can go to Mongo and say, hey, do you have what I'm looking for? If you do, update me, and then Redis can respond then. And what's great about that is, let's say you're typing in something that nobody has looked for in a while, but it's in Mongo. It'll grab it, update Redis, and if anybody's looking for that right after you, well, now it's in Redis, right? You can just serve it directly from the cache. So pretty neat. Yeah, so this is our system architecture so far. So we have the Prefixy app server living in the middle of this. That's kind of orchestrating everything. It's handling, taking requests from a client and issuing responses and talking to Redis and Mongo to get its data. We also built a little CLI to be able to do some administrative tasks, do like a mass import of completions or just maintenance of the data. So how do we turn this into a service? How do we sort of, now that we have this sort of basic thing that can take in completions and prefixes and make this into something that people can incorporate into their own applications? So in order to do that, we needed to be able to somehow namespace and or namespace the tenant data so that if you're using this on your site, that people who are using your autocomplete, that those results aren't mixed up with somebody else's. So for that, we needed to be able to create sort of a token workflow to create unique tenant IDs. So let's say we have Jane. She's an app developer. She visits our token generator to get a JSON web token, which is going to have a unique tenant ID in it that she is going to be able to use in her client. So she puts the custom script into the front-end code of her web application, and every time it's sending its GET request to Prefixy, it's going to send a JSON web token along with it, which then we can use to unlock her data on the back end. So her request, or somebody's typing on her site, so somebody typed in the letter C, that request is coming through. Prefixy can then decrypt it to get her tenant ID, and then use that to access only the prefixes and completions that are associated with her token. So on the back end, how we did this is we prepended every prefix with the tenant ID in Redis, and then in Mongo we allocated a collection to every tenant where we can have all of their prefixes. So in order to basically allow for multi-tenancy, we've added this token generator, which shares a secret with Prefixy so that Prefixy can decrypt those tokens and make sure that all those requests are valid. All right, so we haven't really looked at any code yet, so we'll just do a quick little tour of some of the client code we have, and we'll dive into the search and increment function, just kind of look under the hood a little bit. So when a user types into a search field, this value change function will fire, which will grab the input or the value in the input field and invoke this fetch suggestions method, which is going to send a GET request to our Prefixy app. Once it gets a response from the Prefixy app, this jaw callback is invoked, which basically just takes these elements and adds them to the DOM so that the autocomplete just works. All right, so this is the search function in the back, and it looks like there's a lot going on, but it's actually fairly straightforward. So we have given a prefix and a tenant. What we do is first we normalize that prefix. So we accommodate white or adjust for white space and casing, and making sure it's sort of consistent with all the other completions or all the other prefixes that we've stored. And we prepend the tenant to that prefix. And then we say, hey, Redis, give me all the completions that match that prefix. And if the result of that happens to be 0, then we say, all right, Mongo, tell me if you have this. And if it does, it'll update Redis, and then we'll return the result from that. So that's search. Our increment function, basically given a completion and a tenant, we're going to go ahead and first extract all the prefixes out of that completion, right? So if we have a string like apple, we have to slice it up into A, AP, and so on. And then we initialize some commands that we're going to send to Redis, and we'll iterate over every single prefix that we've extracted from that completion. And in order to maintain our bucket limit, we've got to check how many completions already exist for that prefix, and whether or not it already includes our completion. If that's not the case, or we're over the limit, or we are over the limit, then we'll have to do the logic we talked about earlier, where we boot out the lowest scored item and add +1 for the new completion. Otherwise, we can just add it. Then we send the command to Redis to make these changes, and once that promise is fulfilled, we then call, I guess technically it could be a thunk, that basically then persists those prefixes to MongoDB. So we had a lot of fun with ES6 and some of those features, and a lot of great asynchronous bugs, which were a blast to debug. So some future plans, right? So right now, like the multi-tenancy piece and the way we do that with the token is very bare bones. And it'd be great to have some configuration options, right? Like somebody might want a longer L, right? They want longer prefixes for their application. Maybe they want a way to import completions other than like just typing a lot themselves, or remove them or add them to some sort of filter. So little quality of life things like that would be something we'd like to add. The other thing we want to think about is, as we get more inbound requests, is scaling Redis to minimize cache misses. And so kind of figuring out what the right balance is there, and what we're happy with in terms of, how much do we, is it like 80% is okay, 90% is okay? So kind of figuring out where that line is will be something we'd like to do. The other thing that we thought about that could be interesting is Redis allows for Lua scripting, which we could do or use to basically reduce network requests and have Redis communicate with MongoDB directly and really be a write-through cache, rather than right now where we're always coming back to the Prefixy app. And then last, we thought it'd be nice to have an API rate limiter. So if somebody falls asleep on their keyboard, that all those key presses coming through aren't just blowing up the Prefixy server. All right, that was Prefixy. Thank you for listening. If you have any questions, I'll take those in a little bit. And again, my name is Walid Wahed. I worked on this with a couple other developers. If you want to know more about the project or play with it yourself, you can check it out at prefixy.io. You can generate a token and throw it on an input field if you like. It's my contact info if you'd like to get in touch. I'm also currently in the job market, so if that's something you'd like to talk about as well, I'm all ears as well. So thanks again. Oh, I guess, any questions up front? Yep.
Okay, first thing, which assuming you're using Node.js.
Yep, we have
which Redis client were you using? Because one I usually use, I have to promisify everything.
Yeah.
To get a sync, so a CEOs is
Right, we use Bluebird to promisify everything in the Redis client. I think we just used the node. Yeah. Yes.
So certain words are a lot more common than other words, such as you, are, those kind of words.
Right.
How do you account for that? Because those always show up more frequently than words I'm actually looking for, right?
So you're saying there's certain words in the English language that come up more often than others?
And they're not necessarily words I want to show up in my autocomplete. I don't need the autocomplete for the word ARE, right?
Yeah, so I think the idea is that like what the kind of results you would get in an autocomplete probably like the popularity of a result in an autocomplete is probably not that closely linked to like how popular like a general word is in general usage, right? Because like if I'm on Google, I'm probably rarely typing in like a normal sentence that's pretty specific to what I'm looking for, like video cameras or something, right? So I think or to answer your question, we don't have any sort of special logic for sort of screening certain completions over others. The idea of being that we want like what is popular to kind of emerge organically over time based on how people use it. Yeah.
For your prefix search data structure, is there any reason why you didn't break up each node as an individual letter, considering there's only 26 letters in the English alphabet? And then as you go down, as you traverse the search, the time complexity would only be the length of the word you're searching, because if it's like C and the next is A and the next node is R or something like that.
Yeah, so the primary reason we didn't like implement like a traditional try was because we wanted to be able to take advantage of just the natural fit of like a key value store. And so by mapping sort of the whole prefix, we were able to use that prefix hash tree data structure, which is kind of I mean, it's, at the end of the day, it's a hash table, but the way you can look up any given, right? So like the idea was that the amount of space that we would save from like having a few characters less on a prefix is pretty much trumped by the amount of space we use for all the completions anyway. So just the ease of use of that data structure ended up being a better fit. So, but yeah, we definitely thought about, like, how can we actually just use a try, and it was hard to implement in terms of like a data store that naturally supports that data structure natively. Yeah. Yep.
I have a couple of questions. The first one is, do you decide on what's the bucket size that makes the most sense for usage?
Yeah, so we like I said earlier, we got that idea from one of the creators of Redis, and he recommends you want to have like 300 terms. But we thought that was too much. So in our version, we actually just use 50. And I think it's something where like that would be like one of the configuration options that we would probably want to enable. So if somebody wants like a really fine-grained popularity ranking of the things that people have typed in, we could have I don't know, like 300 or 500. But the idea is that you want to have more than like just a few in order to be able to have the ranking, like something that's not that popular, but just is starting to be popular, that can kind of bubble up over time. Yeah.
And then the other question is, do you think that this is an English language specific thing, or do you think it can just be applied to any languages?
I mean, right now, it's just yeah, I think it would work. I don't know. We actually, that's a good question. We haven't tried it with like like alphabet or alphanumeric characters, or I mean, like it's worked with symbols. Right now we don't screen out any symbols. We really only adjust for white space and casing. So that's a good question. Yeah, I would guess that it might work, but we'd have to test it. Yeah. Yep.
Yeah. What if you want to have a read-only set? Is it possible to implement that?
Yeah, actually, our first version of this project was not dynamic, and we thought, you know, why don't we make it so that you basically give it like a dictionary of all the terms that you wanted to offer as suggestions, and yeah, basically to your point, just be read-only, right? Like it doesn't automatically respond. And there are actually a lot of really good existing open source solutions that offer that kind of autocomplete. And so we thought it'd be interesting to have something where, like in my case, you know, I'm feeling like, well, I just kind of want something that starts capturing stuff and I don't have to do a whole lot of setup and just kind of starts working. So kind of, we wanted something that was just a little bit more dynamic and sort of plug and play, and something that didn't require a lot of configuration. And so kind of the direction we went with this, I mean, certainly it's possible, but I think it's just the fact that there were really good existing solutions out there. We didn't necessarily want to like compete with those ideas.
The actual question is like, if you
Yep.
have to implement that, will your algorithm change or change?
Sorry, say it again?
If you implement a read-only version,
Yep.
backend algorithm, do you think it would change? Do you optimize it differently?
So if we had a read-only version, I mean, basically it would just be about turning off that route in the API so that increments can't come through, and then it'd be, so, I mean, yeah, I guess like that could be another configuration option that we could offer where you basically disable increments, and you would, I mean, like we have like currently sort of in the, for example, in our command line interface, we can like import a lot of completions like in bulk, and kind of exposing that for people as well. Yeah, definitely. Yep.
Have you considered, I don't know, like a safe search option for people writing, curse words or words that are,
Yeah, so that's one of those, quality of life things that we thought about. And I think the easiest thing to do would probably just to make sure that you have a filter on your write actions, right? So that you only put into the data set things that kind of pass that. One of the things we were worried about is like if we have like a really large dictionary that it has to compare against, that could slow that down. So maybe we would have to set up a separate server that could basically handle the screening, and once it's like something passes it, then it could just send like the final result. So that way it's not clogging up the main application. But yeah, and the other part that's difficult is even if you have a safe search, somebody could type in something that's just not very nice, but it's not technically, it doesn't have any bad words in it. So I think something that we would really want in the future is that ability for somebody to remove completion that they don't want, or have just a simple ban list on words that they would, or like just a filter that they would, of completions that they don't want on their side. Yeah. Yeah, but totally, we were we definitely worried about that. Yeah.
Is there a limit to how long a such phrase can you allow to be stored?
I think we have either we don't have a limit or we have a very high limit. Where, because the idea is like, let's say like the Tyrannosaurus Rex sentence we had up there earlier, although it's really long, we chop like what prefixes, how many prefixes of that we use, but we're okay with storing long completions. So, yeah. Yep.
Have you thought about how your data model would change if you were to support partial in-word matching instead of just matching at the beginning of a word?
Sorry, say that again?
Like if you wanted to just match on the letters existing in any word at all instead of at the very beginning.
Yeah, we thought about that. So like, I guess we could, because right now we have like a little action that chops up prefixes. We could probably just do like a suffix tree and just chop those up from the back of the word, so that way any substring would come up as a completion, or like some variation of that. I think would probably work. But yeah, we wouldn't be able to just have a pure prefix, obviously, in that case. Yeah. Cool. All right, thank you so much, guys.
Cool. Thank you, Walid.
Yeah, thank you.
This is yours.
Oh, yeah.
There you go. Up next, we have Rachel. Rachel actually works here at Microsoft, and she actually got us to